Running the exact same foundation model through different development environments results in different execution paths and success rates. This chart compares the performance of a single frontier model. By changing only the environment around it, the success rate on the right scales 6 times higher. This indicates the orchestration code wrapping the LLM drives more performance variation than the model itself. This wrapper is called a harness. It is the architecture that converts a one-shot text generator into an agent capable of observing its own actions and iterating until a problem is solved. Because the harness determines the final success rate, the decision of which model to use is only one part of the performance equation. A harness shifts an LLM's role from generating static text to continuous problem solving. To understand this architecture, we map agent components directly onto a motherboard. The raw LLM is the CPU, processing instructions but lacking memory. The context window acts as RAM, providing fast, limited storage for immediate tasks. External databases function as the hard disk, while tool integrations act as device drivers, connecting the system to outside applications. The harness itself is the operating system. Just as an OS manages resources, the harness dictates exactly what data the CPU sees and the timing of those inputs. It is the primary bottleneck or accelerator for system performance. Researchers at Tsinghua University and Stanford investigated how the representation of this control logic affects an agent's success. The paper proposes building agents using 3 layers of structured natural language. At the bottom is the backend. The middle layer is the runtime charter. The top layer is the natural language harness, containing specific logic for handling failures. The team took the control logic of a desktop automation agent called OS Symphony and translated it from native code into structured natural language. Accuracy increased from 30.4% to 47.2%. More significantly, the total runtime dropped from 6 hours to just 41 minutes. The structure of the logic also reduced API costs. The number of LLM calls dropped from 1,200 to only 34. To find out why the simplified version worked better, the researchers used ablation, which involves removing specific modules to measure their impact on the whole. On SWE Bench, the full harness required 16 million tokens. A stripped-down version achieved the same 75% accuracy, using only 1.2 million tokens. The data showed hand-engineered verifiers and search loops were detrimental. Removing them improved performance by over 8 points. This suggests that adding significantly more verification and structure often interrupts a model's reasoning and increases compute waste. If natural language harnesses are more effective, the next logical question is whether they can be generated automatically. Omar Khattab and his team explored this using an optimization loop. They used an LLM to analyze its own previous failures and then rewrite its own orchestration logic. In this cycle, the agent executes a task, identifies the point of failure in the trace, and updates the harness to avoid that specific error. This automated process requires high-volume feedback, analyzing up to 10 million tokens per iteration. The researchers discovered that the optimization only works if the LLM reads the raw, unedited execution traces. When the raw traces were replaced with human-readable summaries, accuracy dropped from 50% to 34%. Summaries remove the granular detail needed to fix orchestration logic. The signal required for optimization lives in the messy details of the failure. These auto-optimized harnesses eventually outperformed hand-engineered systems by 7 points while using a fraction of the tokens. By optimizing the harness, smaller models like Claude Haiku were able to achieve higher scores than much larger frontier models. Furthermore, a harness optimized for one model successfully improved performance when transferred to 5 different models. These results indicate that the optimized harness is a portable, reusable engineering asset that retains its value even as foundation models change. Anthropic refers to the core philosophy behind these findings as the subtraction principle. Every tool or verification step added to a harness assumes there is a specific task the LLM cannot handle on its own. As models improve, those assumptions become outdated. The extra layers designed to help the model often become sources of friction. For example, when Claude Opus became capable of maintaining its own state, Anthropic removed context resets from their architecture entirely. Most developers instinctively add new tools to fix errors. The data suggests the better approach is to simplify the existing structure. This visualization shows the shift toward architectural efficiency. High-performance engineering focuses on pruning unnecessary modules. If a model can execute a reasoning step natively, any handcrafted structure designed to assist it will likely confuse the process and hurt performance. For engineers building agentic systems, this research provides a practical framework for debugging. When an agent underperforms, follow a specific order of operations before changing your foundation model. First, audit the context window. Removing unnecessary data reduces hallucinations. Second, call unused tools to decrease decision complexity. Third, remove handcrafted verification loops. They interrupt natural reasoning. Fourth, move control logic into structured natural language for massive performance gains. When an agent fails, the most effective solution is rarely finding a larger model. Improving an agent's success rate frequently depends on identifying which structural constraints to remove rather than which model to pick.